Talk about this though, just in general, how we're going to do this. Oh, excuse me. Okay, so what about this here? We're trying to, you got to kind of familiarize yourself with the problem here. So here's H is for hunter, C is for cabin. Evidently, this is the straight river. So he's going to walk along the river for some distance, and then he's going to strike off cross country to get to the cabin. Okay, so it takes him, well, we want to know what's going to be the path he should take to minimize the time it takes to get to the cabin. He can walk, in this case right here, he can walk 2 miles per hour along the rocky land, but he can walk 6 miles per hour along the river. Okay? We know that the cabin is 4 miles away from the river and 7 miles downstream. Okay? So what are we going to do first? It's always our first step. Primary equation. You got to come up with a primary equation. We got to identify some variables. So maybe we can do both of those at the same time. So what is our primary equation going to be? What is the quantity that we're trying to maximize or minimize? Time. Okay, so we want to come up with, we'll call it capital T for time equals what? Okay, so to get there though, what's the variable? What's the thing that we can, okay, the distance along the river. So we could say, for example, that let's call that X. Okay. Or if we want to, we could say, well, that's fine. We can just call that X. That's gonna, yeah, that's fine. We can do that. So if that's X, he's going to walk down river X, and then he's going to strike off cross country. Okay. So what's this distance going to be? Well, it's going to be a little more complicated, but we can find it. Okay, so this distance right here would become 7 minus X, right? And then by the Pythagorean theorem, what would this distance right here be? So this is going to be our red distance, and this will be our blue distance. What's the blue distance going to be? It's by the Pythagorean theorem. Square root
4 squared
of
plus 7
16.
minus x squared.
Okay, 4 squared plus the quantity 7 minus x squared, right? Do we agree? Okay, so those are the distances. Now we got to think about this in terms of time though, right? How we're told we know the distances we can track that their hunter's going to travel in terms of x, and we know the speeds at which he's going to travel. So he's going to travel the red journey at a speed of what? 6 miles per hour, and the blue journey at a rate of 2 miles per hour. Okay, how are speed and distance and time related in general?
Distance over time.
Okay, speed equals distance, speed or velocity equals distance over time, right? Okay, does that make sense? Kind of, yeah. So we'd want to solve that for t, wouldn't we? Right? You guys know the trick. If you have a ratio equation, you can just exchange diagonally in one step, right? Same thing as cross multiplying and dividing by v. So that gives us time equals distance over velocity, right? So really we could break this up into two parts. We could break this, the total time is going to be the time along the river plus the time over the land, right? Everybody agree? Okay. And so the time along the river, that's going to be distance along the river divided by speed. What is the speed along the river? 6 miles per hour. Okay. So this one just becomes x over 6, right? What does this one become? Well, that, right? We could simplify that though. That's just gonna be x squared minus 14x plus 49 plus 16 is 5965. All over the speed cross country is 2. So that's it, right? That's our primary equation. How many unknowns are there? The 4,
Why would you just take that?
leave it out there.
Oh, like take it out of the whole thing, it's just.
Well, okay, but you can't do that because that'd be like saying, right, see, that's not gonna work. We can't say this, the square root of x squared plus 4 is not equal to the square root of x squared plus 2, right? We can't do that, right? We can only factor out a common factor. Okay, so that's what we're stuck with. I mean, it's not, but it is. How many unknowns are there? 1. So we already see that that's convenient. This is time as a function of x, and then really, we can solve that, right? It's not a pretty equation, but you guys have done worse than that before. What's the domain gonna be? Okay, probably greater than or equal to 0, I guess, right? It would make no sense at all for the hunter to travel in the negative direction, right? So, I mean, we know he's not gonna do that if he's trying to minimize time. That would be foolish. So, at the very least, he would just strike off directly for the cabin. So the smallest value of x that would make any sense would be 0. What would the biggest value of x that would make any sense be? 7, yeah. He might go all the way down and then head straight for the cabin. He'd be a pretty dumb hunter if he went down like 10 and then backtracked, right? That's clearly going to add time. So we can ignore anything greater than 7 and say we know that if there's a maximum, well, it has to be maximum, it's going to be somewhere in there, right? And now you just do calculus. That's what you guys get to do. Okay? So that gets you going on it. Okay? There's another one I want to do too. Let's take a look at an economics one. We haven't done very many economics ones. Let's just, that's kind of blurry. So let's kind of leave that one. I'll put this video up. You can go back and look at that video later if you want to, but that ought to get you going on that question. Okay, what about this? This is this is actually a pretty kind of an involved economics problem, but we can do this. Assume that the amount of money deposited in a bank is proportional to the square of the interest rate the bank pays on this money. Okay, furthermore, the bank can reinvest this money at 12%, right? How do banks make money?
Interest.
Right, what do banks do? They give out loans and they pay a relatively small interest rate to people for the luxury of getting their money, and then they reinvest that money and they make back a higher interest rate. And so the difference in the interest rates is all profit to them essentially, right? Minus their overhead costs. Okay? So if we're just talking about this really isn't profit in a way. Well, I guess it kind of is. I mean, they're not taking into account the cost of the workers or anything like that, but in this bank, people love it so much they work for free. So that's a good thing, I guess, for the bank. So if the bank can reinvest the money at 12%, find the interest rate that the bank should pay to maximize profit. We'll just use simple interest formulas. So then what's this going to be? Our profit is going to equal what? So the amount deposited in the bank determines how much the bank makes, right? If the bank can reinvest the money that's deposited at 12%, how much money is coming in? What's going to be the revenue? How do we say that? They reinvested at 12%. So, well, okay, that would be but the money isn't really theirs. The one part isn't really theirs, right? That's owned by other people.
Yes.
But the 12% is. Say it again.
So the 12% or 12% minus the interest rate
Exactly, yeah, so Nick, just amend that slightly. What's the revenue gonna be? Not 1.12, but 0.12, yeah, 0.12, right, times, we'll call it D for the amount that's deposited. Does that make sense? So 0.12 D is gonna be our revenue. Now we gotta subtract from that our costs. So what's that gonna be? You were on something there. So if the interest rate, that we'll call it X, that'll be our variable that we're gonna control, right? The interest rate that we're paying out to customers. So just be, okay, we won't worry about that part yet. For now, it's just gonna be X times D, right? Okay, but now we've got two unknowns there, don't we? We've got the amount deposited, which is not known, and we've got the amount of interest that we're gonna pay, which we're calling X. And let's define those variables. So D equals amount deposited, X equals interest rate paid out. Okay? We got to get rid of one of those variables, so we must have some other secondary equation. Where's that going to come from? The constraint, yeah, what is that?
The square.
Okay, it's this thing up here. Assume that the amount of money deposited in a bank is proportional to the square of the interest rate, which makes sense, doesn't it? You're going to hunt around for the bank that gives you the best interest rate and deposit there, right? So what's that telling us? That's telling us that the amount deposited is proportional to the square of the interest rate. Okay, so how do we write that as an equation? Proportionality? Okay, good. We would just say D equals kx squared, where k is just some constant of proportionality. It's just some constant that's got to be greater than 0, right? Okay. So we could make that substitution, though, couldn't we? There's our equation of constraint, or our secondary equation. We could substitute that in for our d's. Okay, but k is a constant, right? We don't know what it is, but it's not probably important, right? Well, and we'll see it. If it's not important, the math gods will take care of us, and it won't show up in any of our solutions, right? Okay, so what do we get then? If we combine those things, we're going to get P equals 0.12 times D, which is kx squared, good, minus x times D, which is kx squared, right? And so if we simplify that, see, that's going to give us 0.12k x squared minus k x cubed, right? So now how many unknowns are there? How many independent variables? 1. So we got what we wanted. Now we've got our primary equation as a function of a single variable. So what's our domain going to be? Because now we can shift into calculus mode and just make a table and do this, right? So x represents the interest rate. Can't be 0 or no one would invest, right? So it's got to be greater than 0. Is there an upper limit? There really isn't. I mean, there's clearly too big and we're not going to make any money on this thing, right? But there really isn't any defined upper limit, is there? So we're just looking on that domain. Okay, so now we're just going to differentiate and make our table, right? Interpret this. So what's next? Differentiate. So what's P prime? Remember, k is a constant, right? So really I've got a constant times x squared. What's the derivative of x squared? Yeah, so it's going to give me what then? 0.24k times x minus 3k times x squared, right? Okay, so when is p prime going to equal 0? When what? Yeah, so when the equation we've got, then if we set this whole thing equal to 0, okay, one thing we could do, divide both sides by k, right? So the k's go away. We could multiply through by -1 if we want, flip those signs around, and now I can factor, right? So I end up with 3x squared minus 0.24x equals 0. I can factor out an x. And then what am I left with? 3x minus 0.24. So what are my first derivative critical numbers then? 0. Okay, so either x equals 0 or x equals, so what is that? 8? 0.08? Okay. Which of those are going to show up as valid critical numbers in our table? Only 0.08. 0 is not included, right? And then do we want to take a second derivative? Definitely, it's a polynomial. Why not, right? So our second derivative is, from there, what do we get? Minus 6kx, okay? Good. And so now we can make our table. All right, so let me grab all this stuff. Oops. So there's our summary of everything we did on the other page. Let's make our table. Got our domain. What's our only interior critical number? 0.08, which was a 0 of the first derivative. What are we going to get? What sign are we going to get for the second derivative there? If I plug in 0.08, I'm going to get negative, aren't I? Right? Because remember, k is a positive constant, so it's definitely going to be negative. I'm going to get negative 0.24k. Yeah, is that right? Okay. So what does this have to be then? If I have a 0 first derivative, that's horizontal tangent, negative concavity, it's a maximum. So there's only one maximum anywhere. So that's got to be our maximum, right? Our absolute maximum. So 0.08 is the interest rate that we're going to charge. Right? Make sense? Okay, there's one other kind of problem I want to take a quick look at, and then I feel like, man, we've gone through about everything. I want to go through one, like a weighted surface area. Okay, here we go. Okay, this is the kind of problem that I value. I think this kind of thinking will serve you well later. So I want to take a close look at this. So we're going to do problem 40, which means you got to read problem 39. So a solid is formed by joining two hemispheres to the ends of a right circular cylinder, right? So it's like, what's that going to look like? It's going to look like a deodorant roll-on. That's what it's going to look like on both ends, right? Does that make sense? Okay. So the total, well, actually, we won't take into account what the total volume is, but the shape is going to be like that, right? So in problem 40, we're doing an industrial tank like that. So it's got hemispherical ends and a tubular cylindrical midsection, right? Must have a volume of 4,000 cubic feet. The hemispherical ends cost twice as much per square foot of surface area as the sides. So we're trying to not find the dimensions that minimize surface area this time. We're trying to find the dimensions that will minimize cost. So this is what I would call a weighted surface area problem, right? Because you're not really trying to minimize surface area. You're trying to configure the area in such a way that you can enclose that volume as efficiently as possible, keeping in mind that the surface area of the end caps is effectively doubled, right? Because they cost twice as much? Yeah, they cost twice as much, right? So it's more important to minimize the area of the end caps than it is the other part, right? Okay, so what do you think? What do we need here? Probably picture would be good on this one, so we can kind of orient ourselves. So the picture is going to look like something like that. What could we call our variables then? What do you think? You pick, it doesn't matter.
H is the surface area of the hemispheres.
Okay, how about H is the length or the height of that part? What else do we need? Radius. Yeah, we need a radius, aren't we? We need a radius. And the radius is both the radius of the hemispheres and the cylinder, right? Okay, so we're trying to minimize cost, all right? What's the cost going to look like here? So our cost function,
This is surface area.
okay, so it's going to be the area of the two hemispheres. Now, one thing that's kind of nice, the two hemispheres combine to what? A sphere. Good. So we're going to have the area of a sphere, the surface area of a sphere, of our sphere, times what? Well, okay, plus, we'll call this the lateral area. The lateral area of the tube times what? Do we know what the cost is per unit area for the lateral area? We don't, right? They don't give it to us. So what should we probably call it then? Well, we could call it x. X sounds like a variable. Is this going to be a variable or a constant? It's going to be a constant. It's not going to change. We don't know what it is. So how about k? Right, so we're going to multiply k times the lateral area. And would you agree that that's going to represent, then when we do that, that's going to represent the cost for the tube, right? And really what we said there is k equals cost per unit area for the tube. We just introduced that. We don't know what it is, but if the cost per unit area for the tube is k, what is it for the end caps? 2k. Does that make sense? Okay. Is the k going to mess us up, do you think? Because we don't know what it is? Probably not, right? Probably not. When we think ahead a little bit here, when we end up doing the calculus and we're trying to find the critical numbers, what are we going to end up probably doing with that k? Well, either we could if we knew what the number was, but we could also just probably divide both sides by k and get rid of it when we set it equal to 0, right? So it's the math gods will take care of us here. Okay, so there's going to be the cost for the caps. Okay, so what is the surface area of a sphere? Remember? 4/3 pi r cubed is the volume. What's the surface area?
Oh, well,
Mm-hmm.
4 pi r squared.
4 pi r squared. That's it. Okay, so there's the cost for the end caps. What's the lateral area of the tube? What is it again? So think about it this way. Here's an easy way to think about this. If we're just looking at the tube,
Isn't it just h times circumference?
what if this is like a toilet paper roll, right? What if I cut this thing vertically and unroll it? Then it looks like that, right?
Is it just h times circumference?
Yeah, right, so it's going to be h times circumference, right? If I cut this thing and unroll it, then would everybody agree that this distance right here is just 2 pi r, right? And then the height is just h, right? So h times 2 pi r, 2 pi r h, okay? Okay, what's the problem there? Two variables. We need an equation of constraint, but we get one, right? Where's the numbers show up? Ah, there we go. So we get the number, must have a volume of 4,000 cubic feet. Well, what's the volume of this shape? It could be the volume of the cylinder plus the volume of the sphere, right? So we end up with 4/3 pi r cubed plus, what's going to be the volume of that cylinder? Just think about carving out a space. We got the area of a circle that we're going to extrude through space to create a volume. So pi r squared times h, yeah, okay, good. So 4/3 pi r cubed plus pi r squared h is 4,000, right? There's our equation of constraint. Now what's going to be the obvious choice for our substitution variable here? H, right? Definitely H. How come? Yeah, okay. It shows up once there and once there. The R's show up as a squared and linear. That's bad. And R would be tough, right? We don't want to solve for R. So we'll solve for H and make that substitution. So solving for H, what do we get here? Why don't we, to get rid of that darn fraction, let's just clear the fractions here to begin with. What's that mean? Good, we'll just multiply everything by 3. Good. So we'll change this to 4 pi r cubed plus 3 pi r squared h equals 12,000. Now we'll solve for h. So h equals 12,000 minus 4 pi r cubed all over 3 pi r squared, right? And we can make that substitution. Okay, and then we'll have, it's going to look kind of ugly, but we're going to have a single equation that we can solve, right? We can do calculus with. Okay, we'll have a cost as a function of a single variable. So that looks like cost equals this term. We could just make that 8k pi r cubed plus 2k pi r times all of that, times h, right? Well, at least one good thing happens. What's that? Right. You can do that. Okay? And then we get, well, we'll pick this one up later. We got a good start on it at least.